Hello everyone. So in this episode, we start to introducing more advanced topics relating to RF current probes. As you can see here, I have a pair of current probes. Okay, this is a pair of RF current probes that I asked the manufacturer to basically manufacture this pair for me. So in terms of the transfer impedance, this pair of TPCP2500 have exactly the transfer impedance between the two, with the error, the difference between the two is about 0 point something dB difference. Okay, and this pair of RF current probes prove to be a really useful set in troubleshooting tricky EMI issues, right? So that's why I'm going to introduce this subject. But the first thing is, when you get a pair of RF current probes, you got the manufacturer data sheet, you compare with them, right? And then they show exactly the same transfer impedance. But you still need to validate it, right? And so this setup actually shows you how I normally validate a pair of RF current probes to see how matching they are, right? As you can see here, I've already placed the other set of the pair here, right? So this measures the common mode current on the mains cable. And to make sure that I have the best measurement results, I place some insulation paper here so that the cable sits right in the center of the RF current probe. This also would reduce the E-field coupling in a way. Okay, so I'm gonna place this RF current probe next to it. So in the sense that these two measure the same signals. Okay, and don't forget, this pair actually has directions, okay? So in that case, I'm gonna place this one the same direction as this one, okay? So making sure that I have really good, okay? So you can see the current probes are placed, and also as a comparison, I'm using this 100 megahertz DC-AC Hall effect current probe, also measuring the same common mode current. So you can see here it's measuring the common mode current on the same wire. Okay, right. I'm gonna make this also close. Okay, all right. And the DUT, as you can see, again is the same DUT we have been using in this episode. So I'm not gonna explain it. Right. So as you can see, we have three channels, right? And channel 1 basically is the Hall effect current probe, and 2 and 3 RF current probe. And I also place the transfer impedance into the scope so that they will give me the true current reading rather than voltage reading. Okay, I'm going to power the unit up. Okay, so the unit is now powered up. Now you can see the current measurement. Okay, so we see three different results, right? And we're going to compare basically. So the first is I'm going to stop this, right? So that makes things a little bit easier. And first, as you can see, that the DC Hall effect current probe really was struggling, right? Because first you pick up lots of noise, like this background noise is showing here, and also if you look at this higher frequency range where you have lots of things going on here, it was really struggling to pick up the current waveform like these two. Okay, so that's just serving as a comparison. So I'll put in here, right? Now if you look at these two probes, right, you can see, okay, in fact I'm going to disable channel 1 for now, right? So you can see in terms of the shape, they are almost identical. And then I can move this up and down, and then you can see that in terms of the alignment, they are almost matching. So let's have a look at the details, okay? Because these are really what is important, is the higher frequency thing, right? Can we move it here? Yeah, let's put in the center, and then really zoom in, right? And you see, in terms of the waveform, they are very similar. However, one has slightly advanced angle, or you can see the other one delays the other trace by a few nanoseconds, right? 1 or 2 nanoseconds. Right? This is because they are not really in the same location on the wire. These are RF currents, so they will have slight different phase shift. The RF current flowing on the mains wire will have some phase shift, right? In order to prove that, right, let's do a quick one to prove it. So in this case, just remember that channel 3 is leading channel 2. Okay, channel 3 is leading channel 2. So I'm gonna just quickly swap these two to see the results. Okay, so now I just quickly swap these two. So, right, so now if we power it up again to see which one leading which. Okay, so this is previous case, remember channel 3 leading channel 2. Okay. Okay. Stop this now. Put in here. Now you can see channel 3 now lagging channel 2. So we know that, okay, so this a little bit of lagging is natural, not really because of the current probe not matching with each other. Okay, so yeah, so hopefully this quick demo demonstrates you how this pair of current probes work and how they match with each other. Now with the information of this, let's just do another interesting study, right? So now I'm going to disconnect one of the channel, okay? Since we know that they are really matching with each other, right? I really wanted to understand the common mode current in such a converter, right? We know this is a GaN device, right? Based AC to DC converter. So I wanted to see the current really to understand it from the primary side and the secondary side, right? You got the primary side, high voltage, secondary side is the low voltage. And again, in this case, I make the two marking the same direction, so I'm measuring, they have the same polarity in a sense, right? So let's have a look at the current waveform. Okay, so again, I'm going to run it. All right, let's have a look. Okay, so this is again the currents picking up, but now they are measuring the primary and the secondary side of this AC-DC converter. Stop it, right? And let's have a look at the current waveform. So you can see first the current waveform slight difference, right, between the primary and the secondary side. And also, if you look at the higher frequency content, they are also different. This is again because of the RF current have a what we call standing wave on the cable. But what is interesting is you can almost treat these two, right? You can see that really the current, in a sense, flows from the primary side, then cross the transformer barrier, and then gets into the secondary side because the two waveforms showing the same phase, right? It's not like one inverse the other, right? If it's one if one waveform has 180-degree phase shift to the other, that means both current will go into one place. Whereas in this case, you can actually see the current flowing from one direction to the other, or it could be from this direction to the other. But what we can see from the common mode current point of view is that it will flow from one side and then leave from the other side. And that's how common mode currents flow in such a typical circuit.